Welcome to the Prime Research Lab. In this video, we present a clear and accessible overview of the prime counting function, its classical approximations, and our new experimental estimator known as OD-28. The goal is not to reveal technical details, but to offer an honest, transparent view of why prime counting is so central in modern mathematics and why constructing a highly accurate model is so difficult. The prime counting function, written as pi of n, represents the number of prime numbers less than or equal to a given value n. It grows slowly and irregularly. Primes become rarer as numbers increase, but they follow a remarkably stable natural pattern. For over a century, two main approximations have been considered essential. The first is n divided by the logarithm of n, a simple model that captures the general trend but tends to underestimate the real number of primes. The second is the logarithmic integral, Li of n, a far more accurate estimate that has been used as a benchmark for decades. Both are excellent but not perfect. Since the distribution of primes is crucial in cryptography, compression, numerical analysis, and theoretical research, many mathematicians have attempted to develop even more coherent models. Over the last few years, we have been developing an experimental estimator that we call OD-28. It is not a closed formula, and it is not a shortcut to solve deep problems. It is the result of thousands of tests, comparisons, and numerical verifications performed over increasingly large intervals. OD-28 is a data-driven model built by carefully studying the internal structure of the growth of pi of n and comparing it with real values up to extremely large powers, such as 10 to the 29. The graph shown compares four curves: the exact prime counting function, the logarithmic integral, the classical n over log n estimate, and our OD-28 estimator. The key point is this: OD-28 does not outperform the logarithmic integral, which remains the most accurate classical estimation. However, our model has an interesting property. It maintains an extremely low relative error even at very large scales. More importantly, this error does not behave chaotically. It stays within stable, predictable bands. This makes OD-28 a potentially useful tool for fast analysis, consistency checks, and comparative density studies. It is essential to emphasize that OD-28 does not prove anything about deep conjectures such as the Riemann hypothesis, nor does it present itself as a final solution to a millennium-old problem. It is a careful, empirical, documented model that increases in robustness as new data is added, and that works especially well for large-scale numerical exploration. On this channel, we will publish updates, visualizations, comparisons, and thorough tests of the model, along with educational explanations for students and enthusiasts. Our goal is to provide clear, verifiable tools without sensationalism, and to contribute to research with transparency and rigor. If you find this topic inspiring, subscribe to the channel. Welcome to the Prime Research Lab, where numbers truly speak.